Hello and welcome to the first of what I hope to be many Piper Pods. Today, decided to talk about fluid physiology. The reason I've chosen this topic is because over the years a lot of people have asked me a lot of questions and there seems to be a lot of confusion around fluid physiology. So as most of you are well aware, the body is broken up into different compartments, many individual different compartments, but they can be broken up into the extracellular or the intracellular space. And the main focus of today will be describing the relationship of how these spaces interact and then how that knowledge can influence our choices in fluid resuscitation and why we make certain choices. As a breakdown, most of the fluid within your body is found in the intracellular space. That means within the cells of your body holds 66.6% of all the fluid in our body. Okay, now when you consider that 50 to 60% of our body weight is constituted by fluid, that is a significant amount of fluid that you'll find in the intracellular space. Okay, the extracellular space is broken up into the intravascular and the interstitial space. Okay, so intracellular is all about what's in the cell. Extracellular is what's found essentially everywhere else. Okay, so you're talking about lymphatic tissue, synovial fluid, the fluid of your eyes, the fluid found in between your cells, and of course the fluid found in your vascular space. Now I just want you all to take note that the percentage of fluid found in the intravascular space is 1/4 of a third. So that translates to around 8.2 to 8.3% of all fluid found in the body is in the intravascular space. So not a lot, and that plays a big role in our decision of fluid resuscitation therapy. So keep note of that 8% mark for later on. There's other types of fluids in our body that aren't counted within these two compartments, and they're known as transitional fluids. So they're the fluids that are mostly found within our digestive system. Okay, and there can be anywhere between 1 to 2 litres of fluid found within that space. Now when we talk about fluids, we don't want to get confused by talking about water, because obviously water takes up a big component of it, but if we were just had water in our body, as it's quite often said, we're 70% water, it's not actually true. And if it was true, we would cease to exist. So our water in our body is filled with solutes, okay? And these solutes are what's known as ions. And each of these ions contain an electrical current, a positive or negative electric charge. Okay? And these main ions, or electrolytes in our bodies, are responsible for obviously a lot of vital functions within our body, but also a huge contributing factor to how fluid responds and how fluids move throughout our body. So when we talk about fluids shifting in our body, it's not just as simple as filling a bucket with water, putting holes in the bucket and watching it move. Okay, there's a lot of factors that draw, and the main one that gets missed out is the association of these ions and how their ionic charge is actually responsible for a lot of the movements. So the main electrolytes within the bodies, you're all fully aware of them. We've got sodium, potassium, chloride, bicarbonate, calcium, magnesium, and of course phosphate. They're the main electrolytes in our body and the main contributing factors to fluid movement. Okay. Each of these have an ionic charge, and when you hear a test known as an ion gap or a sig ion gap associated with how balanced the body is, then that essentially is what we're talking about, an equation of these electrolytes, both positive and negative, in order to get an idea of ionization. So moving on from ionization, we need to know that there's positively charged electrolytes called cations and negatively charged electrolytes called anions. The reason this is important is because the body likes to have a balance. Okay, so when a cation moves in, essentially an anion has to move out. So when you get positively charged somewhere, you need to be negatively charged somewhere else. Okay, and it's this movements of cations and anions that result in a lot of influences in the body of fluid shifting that we'll get to later on. So I just want you to be fully aware of the actual terminologies before we move on. Now when we talk about minerals essentially don't have, I don't want to say they don't have an ionic charge, okay, because then you'll throw calcium at me and it's like, well, that's a mineral and an electrolyte, and then you get all technical. But essentially minerals within the body, they're mostly associated with being a catalyst of a body metabolism, or being a catalyst of a response. Okay, so that's what happens when we talk about our minerals. And you think about zinc and folate, okay, these are minerals and they have a effect on the body. And yes, they do play a role in fluid resuscitation, but only because of the influence they have on the cations and the anions. Okay, so as alluded to, fluid will move throughout the body all the time in order to maintain balance. Okay, the body's not clever enough to go, oh, I actually need a little bit more in this space, so I'm going to rob from here in order to make this space that little bit better. Okay, there's a lot of contributing factors, and most of the time it does come down just to pure science. Okay, so fluid that you find within the cell, once it gets into the cell, it's actually quite stable. Okay, it takes a lot of stimulus external to that cell in order to make that fluid shift out. Okay, and generally takes a long time, as opposed to fluid found in your bloodstream, which is interchangeable, very, very interchangeable. We lose it in sweat, talking, urination, and also at the capillary beds based on hydrostatic pressure, which you guys should be experts in by the end of this presentation. Okay, so fluid found within the bloodstream will change readily. Okay, will move in, will move out quickly, and any other compartment within the body. The fluids found within the interstitial space, so the fluid surrounding the cells, that's essentially there as a reserve. So it can fill the intravascular, it can fill the intracellular, okay, and is essentially needed as that reserve in order to back up each one of those areas. Okay, it also stops cells leaking and the vascular space leaking as a result of its presence. Okay. Now when we talk about fluid movement only occurs in the presence of pressure. Okay, so it's pressure within the body that allows for fluid movement. But I don't want you to get confused by thinking of pressure in its simple term, like if you exude pressure on something, you're pushing something out. And whilst that's a contributing factor, it's not its literal term. Okay, so we'll talk about different types of pressure within the body and how they have effect on the capillary walls or on the cells in order to encourage movement. Okay, now movement in and out of the cells is done via special channels. Okay, so there's special potassium, sodium, chloride, hydrogen channels within a cell that allow for those particular ions to move in and out of the cell, and as a result the fluid will follow. Unlike the capillaries, which essentially allows for semi-permeable membranes for fluid to move in and out more freely. Okay, so that's the difference that we're talking about when we talk about the different compartments. So moving on to terminology that we're going to talk about. Okay, so now we've got the basis of what the body's made up of, what ionizations have effect on body movement, how it all sort of works. Now we need to talk about the principles, if you will, of movement within the body. So we have 4 terms that we talk about when we deal with fluid movement, and you've definitely heard of these before, but a lot of times people will confuse the first 2, so diffusion and osmosis. Okay, they'll actually get those 2 confused and not really understand how they play a role in each other. Okay, filtration, you've definitely heard of because you've studied the kidney. Okay, and people will often automatically assume that filtration is only applicable when you're dealing with the kidney, okay? But I'm going to tell you today that it's not, okay? And you'll learn a lot more about filtration. And then there's active transport, which is a special sort of movement and what happens within the body in order for it to function with those larger molecules. Okay, so they're the terms that we're going to discuss first. Things that we have to be aware of when we're discussing these terms, things you have to have a bit of an acute knowledge of, is the concept of osmotic pressure and hydrostatic pressure. So osmotic pressure is essentially associated with osmolarity, you've heard that term, or ionic charge within an actual compartment. So an osmotic pressure is not necessarily a pressure caused by mass, it's a pressure caused by ionization. Okay, so that's really big thing you have to worry about, because this pressure, if it's larger, actually has drawing power. So we'll actually add more to it. That's what makes it the most confusing, is we're dealing with pressure, things that were associated with pushing power, but in this particular case it has drawing power, pulling power. Okay, so that's osmotic pressure. Not to be confused with hydrostatic pressure, which is your classic pressure. You fill a pipe up too much, it has hydrostatic pressure, easily understood. Okay, so just keep those two terms in mind as we discuss later on, because it will play a massive role in your diffusion, osmosis and filtration, is if you have a keen understanding of these two terms. Okay, so starting right at the top with diffusion. So diffusion is usually associated with gas, okay, because it's nice and easy. You drop a smoke grenade in a room and all of a sudden that smoke grenade will fill the space. Okay, that is diffusion, because it's moving from a high concentration of where the epicenter of the explosion was, and it'll move to a low concentration the other side of the room. Very simple to understand. You add that in a body, a human term, where we're starting to talk about particles or solutes that are moving from one compartment to another, then it gets a little bit more tricky. So when we're talking about it in the presence of body fluid, the term diffusion means if you have a high concentration of an ion, okay, cation or anion, doesn't matter, of an ion, it is going to result in the movement of that ion from its high concentration into an area of low concentration. Okay, so this is talking about the ions movement, not the water movement. Okay, and it happens all the time. Okay, the ions within a body, if you ingest or get injected with too many ions, then essentially it will move out. It's essentially the basis that contributes towards bioavailability of drugs, okay, is that actual absorption or diffusion pattern of those particular drugs. Okay, how much is it picked up by unwanted cell? Okay, is it protected? So high concentration, low concentration. Talking about solid, if you will, particles, masses moving from one compartment to the next. Now, this particular theory, when you're dealing with body fluids, only works in the presence of osmosis. So diffusion by itself is traditionally not dealing with fluid. But because of the ionization or the concentration shift, it results in a fluid shift via osmosis. So when we look at osmosis, we are dealing with the pure solvents. Okay, so just the watery part of the solution. And the watery parts of the solution will actually move from a low concentration to an area of high concentration. Okay, I don't know how many times I've heard people quote osmosis is from high to low, okay, and it's understandable. Okay, if you have a high concentration on something, you'll think that it would just move, fill an empty space, if you will. But osmosis is referring to the movement through semipermeable membranes as a result of higher concentrations of solutes. Okay, so because a result of what happens in diffusion, the solutes will move to another area. The water will need to follow those particular ions in order to balance them, in order to dilute them. So you have an equal ratio of solvents to solutes, solids to water. So that's the idea. So if you put it in a more of a practical term, if you want to kill a tree, okay, and you pour salt around the base of the tree. So you poured salt all around the base of the tree. The reason it kills the tree is the salt doesn't necessarily go in and poison the tree. The salt will actually draw the fluid out of the ground into the salt. Therefore, the tree can't get any drinks. Okay, when you're in Darwin and you're living in that horrible humidity, and you put sodium bicarbonate in the corner of your room, okay, that's working on osmosis as well. It will absorb the fluid because you're dealing with a high concentration of solvents compared to a low concentration of solvents within your environment, so it will actually draw the fluids towards it, and that is osmosis. Okay, so solutes will have pulling power, and they'll pull the fluids towards them. Okay, so that's osmosis and diffusion. They work hand in hand together a lot of the time. And it usually works best when you're dealing with stationary bodies or stagnant sort of water. Okay, don't get me wrong, it definitely still works within the body, but mostly as a result of osmotic pressure as opposed to the true osmosis. When we deal with filtration, as I mentioned before, it's not just the kidneys. Whilst the kidneys obviously filter via similar means, okay, you have an increase of hydrostatic pressure at the glomerulus, which pushes out the fluids, and then essentially the rest of the process within the nephron happens. You get the reabsorption and you create urine. So it definitely happens. But it also happens in every capillary bed. So obviously each capillaries have an arterial end and a venous end. And depending on where that hydrostatic pressure is greater, it obviously results in different physiological effects within the body. So just going through it, if you have a huge amount of hydrostatic pressure, which is essentially can be translated as increased volume coming into that arterial side, what will happen is at the capillaries being semi-permeable, that pressure, high concentration on the arterial side, will push out into the interstitial space. Okay, and this is essentially what happens at the nephrons. You're pushing it into a concentrated area and it pushes out due to that pure pressure. Okay, now the way you get increased hydrostatic pressure is because it is higher pressure than osmotic pressure. That's the only way you actually get increased hydrostatic pressure. So if you drink a huge amount of water, you've just drunk lots and lots of water, you are increasing your hydrostatic pressure because that water doesn't have any osmotic pressure. Well, I don't want to say any, but it doesn't have a lot of osmotic pressure because it doesn't have a lot of ionization within it. So when it gets diluted with the body, you'll essentially get an increased hydrostatic pressure, which is why you'll go to the toilet. Okay? If you were to right now drink 2 liters of water, your body wouldn't absorb that into your cells. It wouldn't absorb it into the interstitial space. It will go through this hydrostatic pressure and you'll urinate it out. Okay? Hydration isn't quite as simple as just smashing liters of water. As a matter of fact, that's the least recommended way to hydrate properly. But I digress. So hydrostatic pressure is a result of a lower osmotic pressure. Now if you have the reverse, if you have a higher osmotic pressure compared to hydrostatic pressure, then what that is generally saying is you have an increased ionization within that capsule. So because of that increased ionization within the capsule, you are going to draw fluid into it. Remember, the ionization attracts fluids because of osmosis. We talked about it before. It will draw fluid into it. Okay? So that's the difference, and that's the relationship that hydrostatic and osmotic pressure plays together. Now if we think increased hydrostatic pressure on the arterial side. That's normal. Okay, that's a normal state because it's coming out from the heart at a greater pressure. So we can easily theorize that, yep, that makes sense. We're going to have a higher pressure on the arterial side. So essentially, that's where fluid will generally leak out into the body, and it will be easily absorbed by lymphatic tissues or put back into the vascular system on the venous side, and it's all just nice homeostasis. It doesn't really have that bigger effect. If the opposite was to occur, if we have increased hydrostatic pressure on the venous side, now that's unusual. Okay, so if you have a greater hydrostatic pressure on the venous side compared to the arterial side, that is unusual, and that is usually associated with a pathologic state. So if you have cardiac congestive failure, for example, nice classic one, we all know left-sided heart failure results in oedematous feet, oedematous hands. Okay, and here's the reason why, is because you have increased hydrostatic pressure at the venous side, because you have weak heart pushing out the fluid, and it doesn't have enough pressure for the return, so it ends up pooling in that vascular side, and that pooling increase of fluid will increase the hydrostatic pressure, and therefore leak into the interstitial space, sustained leak into the interstitial space, and you'll end up with edema. Okay, the last one that we are going to talk about is active transport. Okay, active transport is what's needed within the body in order to move large molecules. So I mentioned before that cells have channels within them. So not every cell has the ability to absorb every molecule readily. Okay, so your intestinal line has channels perfect for absorbing sodium and glucose, no problems at all, but the cells within your body doesn't have that same channel for absorbing that glucose so readily. So just the presence of glucose is not going to mean that glucose is going to pump into your cell, okay, or out of your cell for that matter. So that's where active transport comes in. So it requires energy, and it often requires a catalyst as well, whether it's a hormone, an enzyme, a peptide. Different molecules, different situations will require different catalysts in order to make it happen. But the point is it goes against the norm. Okay, it goes against the normality of science because it requires energy. So the best way to think of this is if you're in the middle of a lake and you had a boat. You're going out there fishing, all of a sudden the boat gets a hole in it. Normal science response would be for osmosis or diffusion, or anyway, the fluid to move in to that boat. We all know this. Very, very simple. Okay, active transport is you in the boat with a bucket throwing the water back in to the lake. Okay, obviously futile, you're throwing it back into the body of water that's going to end up drowning you, but it requires energy and it goes against science. But sometimes the body needs it, and sometimes you need to go against science as well. Okay, so that's what active transport is active energy use in order to move molecules, and as a result fluids, into a compartment where it is needed most. It is not a natural occurrence. This is a body decision that takes energy and a catalyst to occur. Okay, that seems like quite a lot to absorb as a means of recapping what we talked about. So the 4 different movements, how the relationship works. Okay, now in this particular recap, I'm talking purely within the body and generally speaking, just as a means of letting everybody understand. So hydrostatic pressure. If we have an increase of hydrostatic pressure, it pushes the fluid out. Okay, that is the premise of filtration. If we have a decreased hydrostatic pressure, that really means that we have an increased osmotic pressure. Okay, that's what it really means. So when we have an increased osmotic pressure, we have that pulling power. Okay, because we need that dilution of that concentration. We need the dilution so it has a pooling power, and that is the premise of osmosis. Okay, a decreased osmotic pressure, well, that really means an increased hydrostatic pressure. So then we move back to filtration. Okay, so filtration, osmosis, that's the big premise when we're talking about within the capillary walls. Okay, osmosis and diffusion obviously play a huge role in one another, because if you were to eat a whole bunch of salt, sitting at the pub, you're eating a whole bunch of salty food, you feel thirsty. You feel thirsty because all the sodium chloride is now absorbed into your body and you've got nothing to dilute it. That's diffusion in the absence of osmosis. So what does your body tell you? Well, you need to drink. We need to balance this out with osmosis. Okay, so that's diffusion. And active transport, we talked about that with little man in the boat, but let's talk about it from the body sense. When you eat a massive sugar load before a big game, if you were to just eat a whole bunch of sugar, yes, it will get out of your gut because that's a natural channel, but essentially, if it wasn't for active transport, it would just be excreted in urine, and you wouldn't actually have it in your cells. You wouldn't have it in your muscles in order to be used. Okay, so it takes energy to store that for later. It takes energy to change that particular situation because of the size or the misgradient, but it can happen, but it takes effort. Okay, let's bring it closer to home. Let's talk about different solutions. Now, when we talk about these solutions, I'm talking about putting this solution within the intravascular space. So when we talk about an isotonic solution, essentially what that means is it has a balanced osmolarity with plasma. Okay, that's what isotonic generally means. So because it's already balanced, you put it into the intravascular space, it's not influenced by ionization. So it's not going to move. It's not going to be drawn anywhere. Fluid's not going to be drawn to it, and it's not going to be drawn out of the body per se. Okay, that's the theory of isotonic solutions. Okay, in reality, because now we know a little bit more, we know that that's not true. Okay, because if we say things like that, people can rightly, with that amount of information, rightly assume that if I was to put in an isotonic solution into somebody's vessel, then that entire litre, or whatever we put into them, is going to stay within the blood plasma. Now, because we understand concepts of filtration, we know that that's not going to happen. Because we know osmosis exists, we know that in the presence of filtration, that's going to change the osmolarity of things, and therefore you are going to get fluid shifts. So when we start talking about specific fluids, I'll explain how we get the fluid shifts, but please never be confused by the term isotonic and thinking that there is no water shifting. Okay, there is a lot of water shifting back and forth, but no increased or decrease in overall net movement. Hypertonic solution, on the other hand, they're your low concentration. So this is what happens when you inject water into somebody's vein. Okay, very silly idea, but if you were to just inject water into someone's vein, or an IV fluid like 4 1/5 into adults, okay, that's technically a hypertonic solution. The reason 4 1/5 is a hypertonic solution for adults is because the sodium content is lower than that of the intravascular. So therefore you're creating a lower concentration, which is what the tonic's referring to. So hypertonic refers to a low concentration of solutes compared to the surrounding body. Okay, because you have this low concentration within the cell, so a low concentration, high water count, what actually happens is the water is pushed into the intracellular space. Okay, remember that occurs because of osmosis. Okay, a lot of people get confused with this particular one because they get stuck in that fixation of high concentration, low concentration. So just remember, we're dealing with ionization, and because the ionization ratio in the cell is greater than that in the intravascular space, you are going to push fluid into the cell in order to dilute it, equalize those ratios. So that is what happens when we're dealing with hypotonic solutions. Hypertonic solutions is the opposite. This is what happens when you put high concentration based fluid into the intravascular space. A classic example is dextrose 50%. Okay, it's not the only example. You've also got hypertonic saline, probably a reason why it's called hypertonic saline. Okay, it's got a high concentration. Because it's got a high concentration, you now have increased osmotic pressure within the vascular space, which is going to force fluid to be pulled into it. So it's going to force fluid into that intravascular space. As a result, it can drain fluids from the cells. Okay, yes, can be dangerous. This is how the cellular structures die as a result of tissuing dextrose 50% or calcium carbonate. Okay, why these drugs are so dangerous is because of this pulling power that it has, which ends up killing the cells. Okay, so that's the 3 different fluid types, and that's how they have an effect on the body. And yes, I understand it is difficult to get your head around. Hopefully this has helped a little bit. Let's get down to business. So, 2 sorts of crystalloids that we use. We have Hartman's and normal saline, nice easy ones. I'm not going to go through every type of fluids we use because essentially we're getting too close to the time already. So Hartman solution is classified as an isotonic solution. Okay, so we mentioned isotonic before, relatively equal ionization to plasma. Okay, but it is not plasma. We know this. It's not plasma. It's not a plasma substitute. It has electrolytes. It has lactate within it, which helps. So because of the presence of the lactate, it stays within the intravascular space for a while because of this large lactate. Okay, so lactate being a weak acid has a large lactate molecule that essentially has that staining power, if you will. So it prevents the movements from the blood vessel for a period of time. But eventually, Hartman solution is going to be metabolized. And when it's metabolized, that lactate actually becomes bicarbonate, or equivalency to bicarbonate, about 28 equivalency. But when it becomes bicarbonate, then it's just a negative charged ion. So it can move freely out of the body, and the fluids will dissipate from the actual vessel. It becomes free-flowing fluid. Okay, because it becomes free-flowing fluid, essentially it's now influenced by diffusion, osmosis, and more influenced by filtration as well. So it will move throughout the body. Normal saline, it's also an isotonic solution. Okay, it contains only sodium and chloride and equal concentrations of sodium and chloride. Okay, if that's used for volume resuscitation, which, don't get me wrong, there's a lot of evidence out there these days that says that it's not the best solution to use, especially when associated with hemorrhage. But I digress again, that can be a different speaking point another day. In its purest form, because it has a comparatively high, really chloride level than the actual intravascular space, that in theory prevents it from moving out of the blood vessel. Okay, because it has that high, so you've got that higher focused osmolarity in chloride, which helps keep fluid within the system. Okay, because chloride has a strong relationship with sodium, okay, what essentially happens in the body in the simplest terms is the release of a natriumic peptide. Natriumic peptides are essentially found in the right atrium or in the brain. It's released from the right atrium in the presence of increased fluid. So if you have too much fluid overload within the vascular space, well, actually that pressure on the right atrium will cause a capsule to burst, and the capsule houses natriumic peptide. Okay? If you don't have that, you just have an increase of salt, then essentially the brain releases it. Okay? But the presence of natriumic peptides actually will force sodium out of the vascular space, and with that, the fluid. And then because the concentration will change, the sodium will move. Because the sodium is moved, we've got too much negative, so lots of things will shift around. There's an excellent writing in the show notes that you can have a read of. Because of all this movement of ionization, it will eventually result in free-flowing fluid. Now, the reason this is important is going right back to the start when I mentioned that the intravascular space consists of 8.2 to 8.3% of the total circulating volume, which means taking nothing else into account, nothing at all, just pure basic maths and science, if you were to put a litre of fluid into somebody, eventually, with all the fluid shifting and the equalisation, homeostasis that the body loves to do, you will end up with 82 to 83 mils of fluid left in the intravascular space. That is it. So keep that in mind. Okay, to finish off, just want to put all of this into science and then add a little bit more to the mix for those people that want to understand more. If you've had enough, if you can't possibly absorb any more for now, come back to this later on, okay? Because this is taking everything into account and then adding a little bit of nerdy science to the mix as well, okay? Now, this has purely got to do with the misdemeanor, if you will, or the concept that Hartman Solution isn't safe when dealing with hyperkalemia, okay? So because Hartman's contains potassium, people have led to believe that using Hartman's in patients with hyperkalemia is going to be to their detriment. Now, I'm going to admit, first starting my career, I believe this. I heard this, I've said this, and I may have even, I don't really argue it too passionately, because everyone else agreed with it as well. But I, like many others, made the mistake initially of not realising that potassium itself is not a poison. So potassium is not deadly. Okay? It's the concentration of potassium that causes the problem. So potassium is very helpful, very useful in our body. But too much of it, well, that's not helpful at all. Then you get hyperkalemia, and that's what kill you. So this is just going to go through why potassium is safe to use, but then also a little bit of nerdy science of why it may actually be superior to normal saline itself. So because potassium has a lower concentration or milliequivalent per litre of potassium than what would be considered hyperkalemia, infusing Hartman's, infusing potassium will kill someone. Infusing Hartman's is going to be safe, okay? Because even if you were to replace somebody's entire circulatory volume with Hartman's, which I wouldn't recommend, they're still not going to be classified as hyperkalemic, okay? So that's the reason why it's safe. It doesn't really help with superior, but at least we know that it is safe. The mass behind that, for people who love mass, is if you take a, say, 70 kilogram male, they've got a serum potassium concentration of 6. Okay, most people know that normal levels of potassium within the intravascular space, 3.5 to 5.5. Okay, 4.5 has been written, okay, but 5.5 is generally accepted as a safe level of potassium. So 6 would be considered hyperkalemic. Okay, with that, they have an extracellular volume of 15 litres. Okay, so that's generally what there is. It's 15 litres of circulating volume. And they're infused with 1 litre solution containing 5 milliequivalents of potassium. Their final serum potassium concentration, once everything is balanced out, because remember that's what the body does, would be an equation of 6 multiplied by 15 plus 5 multiplied by 1 divided by the overall circulating volume, which gives you a 5.93 milliequivalents. Okay, so as you can see, it's dropped from 6 to 5.93. So no, it's not a treatment for hyperkalemia in this case. Okay, but it proves that it is safe. You are not going to get an increase by infusing Hartman's. Now, yes, just knowing this, knowing nothing but this, which is I don't recommend, I hope you listen on, then you could argue that normal saline will do the same, but that actually has 0, so you'll get a bigger decrease in your potassium. Okay, but don't be confused by that, because the real science is coming next. This is just proving that it is safe to do. You will not increase someone's potassium to hyperkalemic levels using Hartman's. The real reason that it is considered superior. Okay, now there's two new trials, the SALT and the SMART trial. Okay, really fantastic reads, and they've basically backed up the fact that Hartman's is safe. And they've also looked at the effects of normal saline on acute and subacute illnesses as well. So critically ill, not critically ill, and the effects associated with the use of normal saline. So I definitely recommend a read of that. Okay, but getting back to this, the relationship between chloride and potassium shifting between the cells is present. The movement of ionization throughout the body that will result in chloride moving in and potassium and bicarbonate moving out. Okay, things we need to really understand about potassium is 98%. Okay, that's definitely not a mistake. 98% of potassium in the body is found inside the cell. Okay, so 140 to 155 milliequivalent liters per liters is found within the cell, compared to 3.5 to 5.5 that's found in the vascular space. Therefore, even a small percentage shift of potassium out of the cell into the actual intravascular space will cause massive increases and decreases. So, how does normal saline play a role? Well, normal saline has a phenomenal amount of chloride in it compared to the body. Huge. Normal chloride is around 100, 98. And normal saline contains 154 milliequivalent. So a huge. As a result of this, what happens is you get a non-ion gap metabolic acidosis, or what's been called a hyperchloremic acidosis. Okay, and as a result of this acidosis, potassium will actually shift out of the cell and increase the potassium level. Now, I'm running out of time, so I'm not going to explain the absolute intricacies. Please read these studies, see how it actually works. There is a general rule that I will let you in on. It doesn't happen all the time, but the general rule is that if your pH drops by 0.1, okay, so it goes from 7.35 to 7.25, you can expect up to a 0.6 increase in your potassium level. So as a result of that 1 point drop, you can expect that 6 that we mentioned before to go to 6.6. Okay, and that's a well established or well accepted rule within emergency medicine. Okay, but for the absolute detail of how it works, read the studies. Generally speaking, huge concentration of chloride will cause potassium and sodium bicarbonate to shift out of the cell. Okay, Hartman's doesn't cause acidosis. Matter of fact, there's theories still sort of arguing about it that it might cause a mild alkalization because of its metabolic breakdown into a bicarbonate. Okay, so that is why normal saline may not be the best choice for a lot of things, but in particular, not the best choice for when treating hyperkalemia. Okay, let me know what you think. Please ask any questions. This is my first pod. Okay, so please let me know if this doesn't work for you. Leave your comments, leave your questions. Try to get back to you as quick as I can, and hopefully, if you guys like this sort of thing will continue. Okay, thank you very much. Until next time, take care.